Word up, followers! How we doing, folks? All right, I'm feeling great with this newfound weather system knocking out all of those smoke particles. I hope that where you're at, you've got some nice clean air as well. I'm going to get into this right away, and so what I'm going to be doing is recording this first. I always seem to get these windows popping up when I'm recording. So I'm going to record this first short video that's going to be purely math. So you can see I've got this thing going on here. Partial derivative is an exactness, exact and inexact differentials. This is going to be a bit of a math review. I'm going to try to keep it brief and try to keep it connected to what's relevant to the course. And then we're going to come back to this idea of partial derivatives, exact and inexact differentials in a few weeks. But for now, I want to connect us with this. Okay, so I'll start by saying, suppose we have, get a pen. Suppose we have a function f of xy. Okay, so our function f has dependence on both x and y. Okay, we can write the differential of f. All right, so if I take f prime of xy, I can write that differential by the following in terms of its partials. df, so the total differential of f is equal to the partial of f with respect to x dx, and it is implied that in this differential y will be held constant, but in chemistry we like to put that variable down there to indicate that it's being held constant, okay? Plus the partial of f with respect to y at constant x times dy. So this will be the total differential of f. And if f of xy is exact, so if f of xy is exact, then the following must be true. Okay? I'm going to write all this down and then I'm going to describe what the hell is it that I just wrote. Okay, so let me write these derivatives here and explain what's going on. Okay, so what I have here is if f of xy has an exact differential, then the following must be true. The partial of f with respect to x at constant y. Actually, you know what's a really good idea? What would be a really good idea would be to change colors so I can show you this, okay? Let's get that nice bright red color. Okay, so I have this first derivative of f with respect to x at constant y. Now, if I take the second derivative of this function, but however, I'm taking the second derivative of this function now with respect to y, all at constant x, okay? If this is an exact function, or has an exact differential, rather, then the following must be true. Okay, get the black. Give it to me. Okay, here we go. Then the following must be true. If I examine now the first derivative of f with respect to y at constant x, let's make a little bit of room here, okay, then this all will equal the second derivative in x, all with respect to y. So in other words, what this means, this exact differential means, I can take the derivatives in any order. I can switch the order in which I take them, and the result will be the same. And so note that these really represent second derivatives, right? Okay. And if it is exact, then taking, switching the order, right? So first taking the derivative of f with respect to x at constant y, then taking the derivative of y with constant x. If I change that order of operation and it's equal, we can say it's an exact function. Okay, so let's do an example. Okay, so for example, if suppose that I have, let's see. Oops, here we go. So let's write the function, okay? So suppose I have a function that's f of xy equals ax cubed y plus by squared. Okay? So if I now take the first derivative of f with respect to x at constant y, that is going to give me 3ax squared y, and that's it, because y is constant, so that part drops out. Okay? And now, if I take the second derivative of that, so let's go ahead and do that. Okay, so now if I say partial of y trying to be all slick with different colors, and it's probably just taking up more time. Okay, so now if I do this operation, and of course this is all treating now the other derivative constant, right? If I do this operation, okay. So now what I'm going to do is take the second derivative of this, but now with respect to y at constant x. And so the y is going to drop out, and I just get 3ax squared. Okay. So now what about the other derivative? Hopefully I left myself enough room over here. So let's take the partial of f with respect to y at constant x. Okay. And so now if I do that over here, let's see. So this the y drops out, and I'm left with ax cubed plus, and I'm taking the derivative with respect to y, so that's going to become plus 2by. Okay? And now if I take the partial of x, okay, let's leave my space there, at constant y, of the partial of f with respect to y at constant x. Okay, so hopefully that's clear somewhat. So now I'm taking the derivative of ax cubed plus 2by with respect to x at constant y. And when I do that, that becomes 3ax squared, and then the y drops out. So those two things are equal, so that function has an exact differential expression. Okay? And so how, let's see what I have on the next page. Okay, I've got some more room here. So then now what I got up here is a little Mathematica file, okay? And I just put together several examples here to show, do the following functions have exact differentials? So here are these four functions, a, b, and c. A, b, and c are all just the functions, but you notice I gave you a differential expression for function d, okay? So let's look at how this all goes. So when I'm defining my function a in Mathematica, I can define it just like that. Same with b, and same with c. But now with d, because this function already is a derivative, I only have to take the first, I really am taking the second derivative, but the first derivative of it has already been met. So that's why I separated it into its dx components. So there's dx, which is 3ax squared y. And I also separated it into its y components, dy, which is going to be the a squared y plus 2by. Okay? So I understand maybe if you're not familiar with doing this. So this is how we do this with partial derivatives and exact differential expressions. So now I can do a really cool set of code here in Mathematica. So I'm going to get rid of my suppression of the results, and let me explain to you what I have. First, I'm taking the derivative of axy only with respect to x, right? Then I'm taking the derivative of that derivative with respect to y. Okay, so what do we get from that? So I get 2x. That was a function a. Okay, so what about now changing the order? So now I'm taking the first derivative of axy now with respect to y at constant x. So hopefully you can see how those have been made. They're in a different order. And we get 2x, so function a has an exact differential expression. Okay, what about function b? Okay, some crazy cosines and sines and x squareds and y squareds, but look at that. They're the same. It has an exact differential expression. Okay, perfect. So what about function c? Let's get rid of those results. Okay, so that becomes e to the s for function c and e to the s, so it's good to go. Okay, now look, for this one that already had its first derivative met, here's how this is going. Look, we've got dx as a function of x and y, and I included that ab in there to keep the ab. And now look, I'm taking the derivative of the x component with respect to y, and now I'm taking the derivative of the y component with respect to x. So I'm switching the order, and let's see what I get. Aha! Those two results were not the same. So function d is not exact. So what does that mean? What are the consequences of that? Okay. Well, as it turns out, state functions have exact differential expressions. Okay? So I know these functions here that I gave you are kind of crazy. They're not realistic for the kind of functions we're going to see in this class, but these represent good examples. Okay? We can see that not all functions are going to be have exact differential expressions. So what if it doesn't have an exact differential function? Well, path functions have inexact differential expressions. Okay? So in this example, perhaps a, b, and c would be valid state functions, but function d would be a valid path function. So path functions thus far would be heat and work in context of our first law of thermodynamics. State functions would be U and H. Okay? And there is just one last, a couple last definitions that I want to give. I hope that I left enough room. But I'll give you an alternative form of exactness in the event where we already have a differential expression, which is going to be the case more often than not. So more often than not, we're going to deal with something that's like function d. Okay? So now I'm going to write already df. So it's already a differential. Okay? And I'm going to say that that differential can be separated into x components and y components. Let me write that a little bit more clear. Okay? So there's the function g of xy dx plus h of xy dy. Okay? And so where we note now that the partial of g with respect to y at constant x has to equal what? Think about it for a minute and I'll write it down. Right? So because the first derivative of this function's already been met, okay, then the partial of x with respect to y at constant x has to equal the partial of h with respect to x at constant y. So notice the switching of the order. And thus df would be exact if this is met. Okay? And then finally, another test. There's a few more just properties of partial derivatives that I want to make sure that we remember or are familiar with. There's Euler's chain rule. And Euler's chain rule says in the case we have three variables, the partial of y with respect to x at constant z times the partial of x with respect to z at constant y times the partial of z. What did I do? X, z, and then this has got to be y, and this is z, y. This has got to be x. All of that equals -1. Okay, so this is an important property of partial derivatives, particularly when we have three things to deal with, which we will. Pressure, temperature, and volume, right, will be our x, y, and z. Okay? And then there's also the reciprocal identity. So I'm not going to write reciprocal identity, but I'll just write that the partial of y with respect to x at constant z is equal to 1 over the partial of x with respect to y at constant z. Okay, so these partials can be separated and done, algebraic manipulations can be done with them. Okay, so why does this matter and how does this get connected? Well, here we have this situation here. Look, internal energy on the z-axis. So this is u as a function of v and t. And so now we want to be able to apply this exactness, this test of state function or test of path function. And I'll end it from here and then start a new video picking up with the rest of this stuff, finishing off the first law of thermodynamics. Okay, folks, I'll see you in the next video.